Hello everyone. This video I'm going to show an example for energy conservation calculation. Okay, let's see this example. Okay, this example is a two block problem. Okay, two block connect with a spring and the block one M1 attached to a spring, and its force the spring constant is K. And okay, the other side is M2 here. Okay, well, let's see what's the description of the problem. Okay. Okay, initially M1, M2, they are at the rest. The system is released from the rest. Okay. And then sleep from rest, and let's suppose that M2, the mass of M2 is greater than M1. Okay, then they start at the rest. Okay, and then after release the constraint, the system start to move because M2 is greater than M1. Let's suppose M2 is greater than M1. So when the system start to moving, M2 goes down and M1 pulls to the right. And he said when M2 falls a distant edge, falls a distant edge, and then the whole system stops. Okay, M1 stop, M2 stop. Okay, and why this system will stop? Okay, the reason is here is a rough surface. There is a friction between the M1 and this surface. And then the kinetic friction coefficient is called, the kinetic friction is we don't know the kinetic friction coefficient. He want the problem want us use this information to calculate the coefficient of kinetic friction between the block of mass M1 and the surface. Okay, so this is a very typical energy conservation problem. Okay, and so let's start to analyze this problem. And the calculation of this problem is kind of take a little more time. Okay, and not because it's difficult. Okay, because the reason is you have two objects. Okay, so you have to consider two objects. In previous example, previous example in energy conservation, we only have the one object. Okay, but this problem we have two objects. And so it's take a little more time, so that's why I didn't demonstrate this example in the formal class. So I make this video for this problem. Okay, let's start from this calculation. Yeah, this is the schema for this problem. Okay, initially the mass of M2 is greater than M1. So, they all start from the rest, and after releasing, M2 goes down, M1 pulls to the right. Okay, so this problem I said we use energy conservation. Okay, let's write down the energy conservation. Okay, the formula for energy conservation is delta K. Okay, plus delta U equal to Q heat plus the work done by the external force. Okay, so in this problem, since we have two objects, okay, M1 and M2, so the delta K and delta U, we have to can be write this because we have two objects. So where there will be a delta K1. That means the kinetic energy difference between the initial state and final state from object 1, and we also a kinetic energy difference from object 2, so they can split. Okay, this is the total kinetic energy difference in the system is equal to the difference of each component added together. And also the same, we can the total potential energy difference of the system equal to the potential energy difference of M1 and the potential energy difference the potential energy difference from M2. So and then equals to Q W plus W is and the work done by the external force. Okay. And for the energy conservation problem, I keep stress that or insist that, okay, for energy conservation problem, I'm sorry. You need to first of all just list all the kinetic energy and potential energy at the initial state and final state. And let me see. Okay, and so we have two objects. So let's split it. Okay, the left here we call is M1. We analyze M1, and in this section we analyze M2. So M1, let's see. M1 initial state. Initial state. Okay. M1 initial state. What's the kinetic energy of the M1 initial state? Because I said at the very beginning, these two objects are at the rest. So at rest means there's no velocity, but no velocity, that means there is no kinetic energy. So at initial state, the kinetic of M, I just say, let's just leave the K because I don't want to use too many notation. Okay, let's say K is 0. And what's the initial at the initial state, what's the potential energy of the M1? And for this problem, I'd say in maybe this semester we only have two potential energy. One is gravitational potential energy. The other is elastic potential energy. Okay, so for the so let's first of all let's say gravitational potential energy of M1 at the initial state is, and if we want to evaluate the potential energy of M1 at initial state, we need to set up a coordinate. Okay, and the coordinate, I said if the y coordinate the origin of the y coordinate is here. Okay, this is the green dash line. I said here is 0, and suppose initially the position of M1 is h from h is capital H from the horizon from the origin. So this is M1 G times H. Okay, hope you understand the I believe evaluate the gravitational potential energy. And but be careful because the M1 attached to a spring, So actually, the M1 system has the elastic potential energy. So elastic potential energy, let's say it is U spring. And the problem, I think that initially, M1 and so it looks like I forgot to mention one thing. And initially, M1 rest, and initially the spring is unstretched. Right? Initially, the spring is unstretched. So if the spring is not stretched, so there is no elastic potential energy. So M1, the elastic potential energy is also 0. Okay, and so M1 for the initial state. Okay, so M2, let's also do the same thing. M2 initial state. Okay, initially the M2 as is also at rest, so the kinetic energy is 0. And what's the gravitational potential energy of M2 at the initial state? Okay, the initial state, I say the origin of the y-axis is here. Okay, we say the origin here. So initially, the gravitational potential energy of M2 is also 0 because I set the because M2 is at the origin. So its h is equal to 0, so it's also 0. And what's the spring potential? What's the potential and elastic potential energy of M2? Because M2 does not attach to any spring, so it doesn't have the elastic potential energy of the M2, so it's also 0. Okay, that's for initial state. So and then we go to the final state. Should we zoom in? I should zoom in one moment. Okay, so at final state. So final state, what's the kinetic energy for the final state of M1? Okay, because the problem say after all, yeah, the system start to moving after releasing, and then finally they both stop. Okay, because due to the friction, finally these two objects all stop. A stop means there's no velocity, and no velocity means there's no kinetic energy. So at the final state, M1 is at rest, stop, so kinetic energy also zero. And after an final state of potential energy of M1, let's just suppose the distance here is long enough. So after in the final state, the M1 still somewhere here. Okay, its position for y, its position, its height is still h from the origin. So at the final state, the gravitational potential energy is still M1 GH. And what's the elastic potential energy of M1 and elastic potential energy of M1 at the final state? Because problem say the M2 moves h downward. Okay, that means M1 also moves h to the right. M2 moves h downward. That also means M1 moves h to the right. Okay, moves h to the right. That means the spring stretch h. Okay, because M1 moves to the right with a distance h. So that means the spring also stretch h. Okay, so it will have the elastic potential energy. Okay, I think stored. Okay, so elastic potential energy is 1/2 and k and h small h square. Okay, potential energy 1/2 k times stretch square, the amount of stretch or amount of compressed square. Okay, that's the final M1. And for M2, what's final state? M2 final state. At final state, M2 also at rest, so its kinetic energy is also zero. And what's the potential energy of M2 at final state? Okay, because M2 moves downward with distance h. So at final state, M2 is here. And what's the gravitational potential energy of M2 at final state? So it's mg minus h. Be careful. It's m2g minus h. m2g and times, here you have to be careful, it's minus h. Okay, because in this system, I set up the coordinate, I say the origin of y coordinate is set up as here. Okay, so when m2 moves downward with a distance h, so here the coordinate here is minus h. And the potential energy calculation tells us that m times g times h. Okay, in this coordinate, in this position is minus h, so I have to put minus h here, not plus h. Be careful. Okay, and what's the elastic potential energy of M2 at final state? Sorry. You can see clearly I say before, the M2 it doesn't attach to any spring, so M2 doesn't have any elastic potential energy, so it's zero. Okay, so that's the M1, M2. Okay, initial state and final state. Okay, and then we have something have to figure out is Q and W external. Okay, seems the system is isolated. There is no external force. Okay, so there's no work done by external force. So Wext is zero. And what's the Q? Okay, in the problem I show, the Q mostly from the friction. Okay, because it's rough surface will create friction to this object, to M1, and the friction will generate heat. Okay, so the heat is the friction force times distance, and distance is h, because like I said before, M1 moves h to the right, so it's h. Because friction force, there's no, it's always opposite moving direction, and the friction is only related to the distance, and distance there's no direction issue, so it's always h. And because the friction generate heat, it's generate heat. And I say in my convention, generate heat, that means it generate heat to outside. So it's negative. It's negative. And so the next thing is, what's the friction force of the object? What's the friction force of the M1? And for this problem, because there is no acceleration on the y direction, there is no acceleration on the y direction, and sigma Fy equal to m1 times ay, and the acceleration on y direction, let's assume it just m1 just move horizontally, so there is no acceleration on y direction. That means ay is 0. Okay, so it's 0. Sigma Fy is 0, and y, if in the object m1, you draw the diagram, the free body diagram, you have weight m1g, and you have also normal force. I say you place anything on the surface, you have normal force, and you have, and also here this problem it also has friction. Because right now we only consider y direction, so we just ignore the friction the friction force here. So F sigma Fy equals 0. So that means n upwards positive. So n minus m1g is equal to 0. So let's give the normal force is equal to m1g. And the friction force normally is proportional to your normal force. So it's minus nu knh equals to minus nu kmgh. Okay, so that's the Q. Okay, so we probably have all the information. So let's us put everything together. Let's put everything together. Okay, let me write down the equation for the energy conservation. Okay, delta K1, because we are two objects right now, so we have delta K1, delta K2, and delta U1 plus delta U2 equals to Q plus W work done by external force. So let's start from object 1. Final state minus initial state. Be careful. Final state minus initial state. So it's final state for M1, final state K0, initial state K0. So 0 minus 0. Okay, we don't ignore that. But 0 minus 0 is 0. So what about M2? Initial state, final state, initial state, 0 minus 0, also 0. Okay, so okay. So it's a 0. So okay, we don't consider. So the potential energy difference of M1, final state, initial state. And don't forget, we have right now we have potential energy and elastic potential energy. So delta U1, let's treat this separately. So delta U1, let's start from the gravitational potential energy, M1g capital H, and M1 and initial M1g capital H, the same. And then you minus them, this one minus this one, also 0. Okay, so it's 0. And the spring potential energy, 1 over 2 kh squared minus 0. So 1 over 2 kh squared minus 0. And for object 2, okay, potential energy, let's see, gravitational potential energy. Okay, here is m2g minus h minus 0. So plus m2g minus not minus m2 minus h. Okay, m2 minus h. Okay, and a spring potential energy 0, 0, so it's also 0. So we finish here. The left hand side, you see, it's very actually very. Yeah, like I said, this problem is not difficult, but you have a lot of things to consider. Okay, but it's not difficult. So let's minus the heat. The heat we just calculate. Okay, what's it about heat? Here, minus nu kmgh, minus nu kmgh. So it's minus nu km, and it's m1gh, right? Yeah, m1gh. Yeah, it's m1gh, m1gh. Right, so okay, m1 gh. Okay, and external work done by external force is 0, so 0, 0. So, and what we trying to find? The problem want to us find the kinetic friction coefficient of kinetic friction. So very easy. Okay, we almost get the answers. Okay, so let's make do some algebra work. This will be that we will get mu k m1 gh equal to m2 gh minus 1 over 2 kh squared. And we found we have OH. We can divide it. And finally, what's our answer? Nu K, because that's people, but not people one. It's problem one. We have M1G and M2G minus 1 over 2 KH. Okay, that's the problem one. Okay, I check my answer. Yeah, that's right. Okay, so that's the whole calculation process of this problem. Yeah, you see, the final calculation is not very difficult, but the problem is if it's two objects, so you have to consider many stuff. Okay, and don't forget how to calculate your heat. Your heat is mostly generated by friction, and yeah, so if you can calculate the work done by the friction, you need to calculate the friction force, and you need to know what's the distance. Okay, well, the distance, how distance, because work equal to F times the displacement. Okay, for friction, so you need to know distance. Okay, so and how to find the friction force, you need to do the force analysis. So that's why force analysis is also have to use even in energy conservation problem. You still need to do some energy force evaluation or force analysis. Okay, so this is an example problem for energy conservation. Okay, so I just stop the video here, and we'll talk about other example next time. See you. Okay, see you later. Okay, bye bye, bye bye, bye bye, bye bye, bye bye, bye bye, bye bye. Okay. Hmm. Bye.